In this video, we want to talk about logistic growth. Now, logistic growth is a population growth model which assumes that there is a maximum carrying capacity, that for some reason, say environmental reasons, let's say um, the environment can't support more than so many individuals, right? Just not enough food or whatnot. Um, and so that as you get a bigger and bigger population, the death rate starts to overcome the growth rate so that you don't grow as fast. Uh, it's also a very good um, model for looking at the spread of a rumor or the spread of a disease. So from the point of view of this discussion, because of the world we currently live in, I'm going to talk about the spread of a disease. Rumors and diseases are very much the same, right? You start off with a small number of people that know the rumor or have the disease, and then they interact with people. And if there's two people interacting that know the rumor, it's not going to spread. Or if there's two people interacting that don't know the rumor, it's not going to spread. But if someone interacts with someone who knows interacts with someone who doesn't know, then there's a possibility that the rumor might spread, or that the disease might spread, depending on how juicy the rumor is or how communicable the disease is. Then that rate of spread will be different. So here's what we're going to do. We got exponential growth was our original thing, our original population model, where the rate of change in your population is just some constant times the population. This led to your basic exponential growth. It probably should be C e to the RT. Yes. So, but what we're going to do now, this just allowed the population to go up to infinity. But we're saying, no, this isn't going to be the case, that as you get closer to some maximum carrying capacity, which I'm going to use the letter capital M for this maximum carrying capacity, um, it will, your growth rate will get less, right? So the closer you get to the carrying capacity, the lower the growth rate is going to be. So what I have here is I'm modifying this y equals r, y prime equals ry to y prime equals ry times this 1 minus y over m. Notice when I'm thinking of m as a big number, so it's the maximum number of population that you could have. So let's figure that y is initially small. Well, y divided by m is going to be um, very small, and 1 minus that is going to be very close to 1. And so that this will look essentially like exponential growth. However, as y gets closer to m, this term, 1 minus y over m, as y gets close to m, this thing is getting close to 0, which is saying that the derivative of y is going to be getting close to 0. It's going to start pulling the growth rate down. Okay, so this initially will look like exponential growth, but then it'll peter off into what's called logistic growth. Okay. When I first learned about this, I didn't do it in this form. I saw it in this form, where essentially you factor out the 1 over m and put it with the r out front. Because what this is right here is you then end up with a y times m minus y. Y is the number of people that have the disease. M is the total population. And so M minus Y are the people that don't have the disease. And so when you're trying to figure out how people are interacting, right? What's the chance of this thing spreading? Well, you got to figure out, if I grab two people at random, what's the chances that one of them has the disease and one of them doesn't have the disease? Because that interaction is what's potentially going to pass the disease. So I want to figure out how many of these combinations there are, and then multiply that by the likelihood that that the disease is going to pass. And that's what this number out here essentially was a combination of how many times are you going to get such a combination, and then what's the probability of the disease spreading or the rumor being passed. Right? But it's equivalent to this, which has a different way of thinking about it, mainly that this term is pulling down r as y gets close to m. Okay. Now, in either form, I can see that there are two equilibrium values, y equals 0 and y equals m. This is an autonomous equation. There's only y's over here. There's no t's. So y equals 0 and y equals m are equilibrium values. When I look at the, right, and this is a quadratic polynomial opening downward, right? It's a quadratic polynomial opening downward because the minus y squared would mean it's downward. So I have intercepts at 0 and m, and it's positive in between, and it's negative on the outsides. So I see this downward stuff up above. I see positive slopes in between my two equilibrium values, and then negative slopes down below here, okay, with the equilibrium values. This one I plotted with capital M equals 5. So the carrying capacity is 5. And of course, there's a equilibrium value down there at 0. Okay. Now, let's solve this differential equation. I'll go back to the original version here, written like that. And it's separable, so I'm going to divide both sides by all of the stuff with y's in it, and then multiply by dt to get this. I then integrate both sides. The integral on the right-hand side is easy enough. That's just RT plus a constant. The integral left-hand side, on the other hand, is going to take some other method, and I'm going to do partial fraction decomposition. So recall how we do partial fraction decomposition. We say I can write this thing as a sum of a over y plus b over m minus y. So look at those two factors. I make them independent denominators and put constants over the top of them, and then I try to figure out what a and b have to be. So if that thing's going to add up to this, then if I multiply both sides by this denominator, that cancels out on this side, leaving just a 1, and this denominator times that fraction, the y's cancel out, leaving just a times the other factor. And when you multiply this times this fraction, the 1 minus y over m's cancel out, leaving just a by. Now this has to be true for all values of y, so I'm just picking a couple random ones. Not really random because I'm picking very specific ones. I'm plugging in y equals 0 because that's going to make that go away. And we see then that a has to equal 1. And I'm going to plug in y equals m to make this one go away. And I get b times m equals 1, so b equals 1 over m, which turns that integral right there, knowing a and b now, into this integral down here, which I can integrate to natural log y. There's a u substitution on this one with y equals 1 minus y over m, so the du is minus 1 over m dy. I seem to have left out the dy here. But there's the 1 over m, so I'm just missing the minus sign, hence the minus sign that shows up here. Okay. And then the integral of minus 1 over u du is minus the natural log of the absolute value of u. So there's that. Doing some properties of logs, I can rewrite it like this. And then exponentiating both sides and doing the thing with the e to the c, I get this. Trying to solve for y now, I'm going to, what do? I'm going to take the reciprocal of both sides. Notice that this should really be a 1 over c, but 1 over c is still a constant. The e to the rt turned into e to the minus rt because I put it in the denominator. Then I can distribute the y into both of those, so 1 over y and 1 over, the y's cancel out on this one. So it's just 1 over m. Then add that 1 over m to the other side, and then take the reciprocal again to get y equals this. And then I do one more step. I don't have to, but I'm going to multiply top and bottom by capital M. So that makes the m here. And then the 1 over m becomes just a 1. And technically, the c gets multiplied by the m as well. So this should be c times m, but well, it's just a constant. It's just a different constant. So it looks like maybe all I did was I flipped that 1 over m over with a plus sign there, which is not legal. But it is legal because the m is actually multiplied by that c as well. So the logistic growth model looks like this. And plotting the curves, going back to the original differential equation, when I drew this, I had m was 5, and I think r was 1. So what I'm doing here is plotting solution curves with m is 5 and r is 1. for different values of C. For positive values of C, it turns out I think we get these blue curves in the middle, and for negative values of C, you get the ones that are either above or below. Okay. Uh, if you've been watching any of the data that's been coming in about the spread of this um, coronavirus, um, you may have seen some curves that look like this. It's hard to tell on some of them as you look at different countries that they're still on this part of the curve that looks like it could be exponential growth. But then when you see the one longer term ones, South Korea, for instance, um, oh, there's been other ones that you see that it's going up and then it bends back this way. And the thing is, if you look at daily change in the number of infected people, right? Initially, the number of people each day that are being infected, well, the daily change would be the derivative of this thing. And initially, there's not very many gaining each day, but then through the middle here, you get a lot, but then it starts to fall off again. So that graph of, number of people infected per day grows and then falls back off again. And it's through the middle here where it's the highest. Um, so that's what you want to see. You want to see these curves bending back downward. The state of Washington, I think, has been doing pretty well. I'm making this video on the 22nd of April, and Washington seems to be doing this bend at the moment. The United States in general is still in the midst of this part. It isn't showing any sign of bending back down yet. Um, the world is in a similar situation. So anyway, this is spread of a disease or spread of a rumor, logistic growth. Oh, yeah, the other thing I want to say about it is the whole social distancing thing. What is social distancing doing to this equation? Well, what it's trying to do is it's trying to change the growth rate, right? Looking back up here, we're trying to change R. We're still going to infect just as many people. But the idea is if we could change R, if we could make the rate of growth slower, then we can spread out how long it takes to get in that daily change. And that's the real big thing. Each day, how many more people need to be in the hospital, right? If you can keep that under control, if you can keep that slow enough, granted, it's going to take a longer period of time to infect everyone, but if you can keep that slow enough, you can stay on top of the needs of the medical system, right? I mean, heart disease and cancer kill more people every year than anything else. Actually, right now, COVID has taken over on the daily death rate. But for the year in total, the other two have killed more people than COVID has. But they do it at a slow enough rate that the hospital system can handle it. It's the current huge influx of this new killer that is just swamping or has the potential of swamping the system. But here in Washington, we've managed to do a pretty good job of keeping R down by social distancing and other measures. We are keeping the spread of the rumor, the rate at which the rate at which this disease spreads is low enough that we've been able to manage the hospitals well enough. Now, if we start to go back to our old ways and it starts spreading again, then R gets bigger and this doesn't go more slowly, this rises more rapidly, and you get those increases, those daily increases, which are what really kills the hospital system. So anyway, there you go. Spread of a disease, logistic growth.